Very ambitious title I was given, which was How AGN Work, because I'm not sure I know, and it will probably take an awfully long time to do a talk like that. So I thought I would restrict myself to AGN feedback, and what I'm going to do in this talk is to consider, since people rightly, I think in my view, express scepticism or worry or lack of knowledge of how AGN feedback might work, on prescriptions used already in the literature, I would talk about what physicists do is take an idealized case where you think you can understand everything and then see what physics tells you. So I will try and use that approach here. So the mystery that I would personally like to solve and got me into this business is that the galaxy, or the galaxy bulge, knows all about the central supermassive black hole. This is from Coleman and Ho, but all these things started around 2000. There is an enormously tight relation between the black hole mass and, for example, the velocity dispersion. It goes like the fourth power. And there's similarly now beginning to be almost as tight relation between the black hole mass and the bulge mass. So the question that immediately comes to mind here is, how on earth does the galaxy know anything about this tiny object in the middle? It's absolutely insignificant in terms of gravitation, and so its gravity affects a really ridiculously small region of about 10 parsecs in the middle. So how can there be any connection at all? So the question is, why does the galaxy notice the hole? Well, there is one property of the black hole which is indeed very, very, very noticeable to the bulge. Namely that when you were growing the hole, it released this amount of radiant energy. We know from the Saltan relation that the black hole mass was made of stuff that radiated, and so it's hard to hide this amount of binding energy that's been released, and that's about 1,000 times more than the dynamical binding energy of the bulge. So there is really some strange imbalance here. In fact, it's quite obvious that the galaxy ought to notice the hole because of its energy release, and this is what we call feedback. But you can see there's now a problem, if anything, the other way. It looks as though there's too much energy being released. Well, what's the connection between the host and the black hole? We know that we have supermassive black holes in every large galaxy, or medium-sized galaxy even, but only a small fraction of galaxies are actually active in the nuclei, and that tells you that the growth rates, when they do grow, had better be fairly high. So I should adopt the view that at times supermassive black holes try and grow at the Eddington rate. And to remind you, that's the Eddington luminosity there, electron scattering opacity, and eta is the efficiency with which rest mass is converted into radiation. And what will be important for the rest of the talk is a conclusion I draw from that if you're feeding the hole at more than the rate at which its radiation pressure will accept, then you blow away lots of material, and that gas is going to interact with the surrounding galaxy. So what happens in this case? Well, it was in the classic disk accretion paper by Shakur and Sunyaev in 1973. They considered this, as indeed they considered virtually every problem in accretion disk theory. Annoyingly, it sometimes appears in a footnote or the caption at the side of a figure, but it's all in there if you look carefully. And what they said was, well, if you try to feed this little black hole here at more than it wants to accept in terms of radiation pressure, it will gradually notice, as the material spirals in through the disk, it will reach a point where the local energy release, Gm m dot over r, so just the gravitational energy release, that's already at Eddington. At that point, the disk will say, hey, there's something wrong here. I've got more pressure than I like. I'm going to blow some material away. And what they hypothesized, and what simulations do seem to agree with, is the idea that m dot would then adjust itself just to decrease gently towards the Eddington value exactly at the last stable orbit, and so you would be decreasing roughly linearly. And what that then amounts to is you find that the luminosity rises just logarithmically slightly above the formal Eddington value, but more importantly from our point of view, most of what you fed in that was above the Eddington rate is actually expelled, and you know, since it's coming from quite close to the black hole, it must be expelled at fairly high speeds. And what you can also deduce, it's not quite so obvious from my argument, but it's also true, is that on average photons, which have caused all this mayhem, have scattered about once before they get out. The optical depth is typically of order 1 in an Eddington outflow. And so that means that since electron scattering is front-back symmetric, on average photons give up all their momentum on each scattering. And that translates into saying, well, if you blow out gas at the rate m dot, then the velocity must give you a momentum which is of order the momentum of the radiation field that you started with. So it must be kicking out about that much momentum. What does that mean in terms of energy? Well, you can turn this, take that equation, turn it around like this, dividing by c, and you can immediately see that the speed, as I suggested before, has to be quite high. So I will always deal with cases where this ratio here of out to in is not very different from unity. That turns out to be realistic. It's quite hard to get very high Eddington ratios in AGN. And that tells you that V over C is something like the efficiency eta, so it should be of order 0.1 C. And you can also work out the energy outflow rate. This is the momentum rate. And using that, you can simplify this combination here. And you find it is indeed proportional to the Eddington luminosity. It's a mechanical luminosity, but it's only 5%. It's eta over 2. Remember the 5%. 5% will come back, and indeed does come back regularly, in simulations where people iterate. They iterate this parameter here that multiplies the efficiency of Eddington luminosity, and they find that they need 5%, but actually I think that's a direct consequence of saying you've got an Eddington type wind with that momentum. Well, is there any evidence of this? Yes, there is. There is at least one galaxy now, but there's lots of others which have blue shifted absorptions. This one is particularly cute in that it's a classic P Cygni profile, the blue shifted absorption relative to emission. And lo and behold, you can see, because this is in X-rays, this shift here is really quite enormous, 6 to 7 kV. So indeed, you've got about 0.1 C outflows. It's now known that a majority, I think, of local AGN show winds like this, which are episodic. The reason we know from the column densities that they're not there all the time. They've now acquired the unfortunate nickname of UFO, which is meant to mean ultra-fast outflow, not unidentified flying object. But these things are awfully common, so most local AGN, where you can do anything, have them, and indeed you can show that it's quite plausible that they should appear in X-rays. The ionisation parameter is actually specified by the amount of mass you're allowing to flow out. The fact that so many of them show these outflows also tells you that they're not narrowly collimated. You look randomly at a sample, so there's quite a large number of these things, and therefore they're quasi-spherical. Well, I've alleviated my...
Sorry,
yeah.
The fact that they're common comes from, the argument comes from X-ray spectroscopy of many of those.
So all the local ones you can do, almost all show them.
But they're only, that's for AGN. In AGN, we're
Yes.
already looking at a specific angle towards them.
Maybe.
You
Okay.
can see that structure in the UV lines, which is telling you that outflow is not going very far.
Yes, it doesn't go very far into this, as you'll see. So I've alleviated my energy problem a bit, because I've got down from that to something a lot smaller, 5%, but it's still embarrassingly high. This is still enough to do real damage to the galaxy. So what actually happens? Well, the wind has got to collide with the surrounding interstellar medium, and that tells you it must shock. In fact, there must be a pair of shocks, one to tell the wind to slow down, one to tell the interstellar medium to speed up, and a contact discontinuity between them. So it's the wind shock where all the energy gets released, because that's where it started, and there are two regimes. The regime which will turn out to be important, in fact both will be important for what I say, but initially the regime where the gas cools very rapidly, cools within a flow time, tells you that you lose most of the energy, but what you cannot lose, of course, is the ram pressure. You can't lose the linear momentum, so that remains. But you're reduced essentially just to ram pressure in this case, so-called momentum-driven flow. If the gas does not cool, and we'll see that regime does become important later on, this is effectively an adiabatic shock, or is often called energy-driven flow. And now you've got a hot bubble that's trying to expand not just because of ground pressure, but much greater is the gas pressure, which is pushing against the interstellar medium. And what we know from work by Ostreicher and collaborators back in the 90s is that, paradoxically, this cooling case occurs, amazingly, because there's a quasar in the middle. The quasar radiation field has photons which typically correspond to about 10 to the 7 degrees, or less. And this shock temperature here from 0.1C is more like 10 to the 10 Kelvin. So if you've got enough photons hitting those electrons, and electrons are communicating with the ions, those photons want to cool the electrons right down. And so they're taking away all the thermal energy that was released in the shock. So what that tells you is the initial expansion. Why do I say initial? Because I need the radiation field to be sufficiently intense. So I can't have the shock too far away, otherwise there are just too few photons compared with the number of electrons. So close enough to the central black hole, the shock must be cooled, and therefore the initial expansion into the bulge gas will purely be driven by the momentum, which is this very simple quantity. So here's the picture, there's a quasar in the middle. This is all a cartoon, of course. This green stuff is this purple stuff is the wind. The green stuff is the gas it pushed ahead of it in a snowplow, which is kind of a thin region now because it's all cooled, and that's being swept up. The blue is the forward shock saying, hey, something's happening, and the red is the ambient interstellar medium. So the very simple model you can adopt here, and I don't propose to do the mathematics in detail, but please look at the slides afterwards. An isothermal sphere potential gives you very simple relations, which are generically roughly okay. You can do it with more complicated potentials, and you get essentially the same answers. So you can write down an equation of motion for that shell, whose mass here is linearly proportional to the radius. And as gravity pulling you back and pushing you is just the Eddington thrust. So it could be simpler. You can turn that equation into a rather suggestive form. You isolate all the constants in this thing m sigma, which is this combination here. And you can now integrate that equation once. Very simply, you multiply through by r times r dot. This is derivative of a square. This thing is derivative of r. This thing is derivative of r times r dot, which is r squared. So you can integrate the whole thing like that. And you can see that if your black hole mass is small, m less than m sigma, this term here means that there is no solution at large r. That means that at large r, this side is inevitably negative, whatever the constant was. And that tells you physically the thrust, the Eddington thrust, even the whole Eddington thrust, can't lift the gas against the potential. Gravity's holding it in, so it pushes, and then the shell gets too heavy, and it then stalls and falls back. What happens if this changes? Well, you can see if m is greater than m sigma, in fact this term will dominate and now be positive at large r, and you'll end up with the velocity going to, as it happens, formally something like the escape velocity. So it will actually get going by itself if you left it after a bit. Well, is that relation interesting? Amazingly, it goes right through the points. Without fiddling, it's the worst possible situation for a theorist because it's got no free parameter, and yet it more or less works provided the gas fractions are too different from the cosmological value of about 0.1. So that very, very simple picture tells you that the black hole mass will grow until the Eddington thrust starts to push the gas out. When I say starts to push, it doesn't push it very far. This is all tiny. The scale of all this is typically just a few times the radius of influence, so a few parsecs. So incredibly localized, all down in there, nothing else happening. The rest of the galaxy doesn't know it's going on. So what actually happens at m sigma? Why is it such a big deal? The answer is that once you get to m sigma, remember the whole point was, once you get to m sigma, this becomes positive, so you can start pushing the shell a bit further out. And remember, the shell had to be close in if it was going to cool. The shocks don't cool if they're pushed too far out. So after a bit, you can see what's happened. You worn away at it, and now you push the gas out to such a radius that the inverse Compton effect is now too weak. The quasar's got too few photons out there to cool all the electrons. So inevitably, you end up in a situation where the shock doesn't cool, provided the outflows are still going on. The shocks will not cool, and this is interesting because it tells you the wind shock is now adiabatic, and in particular, that naive little equation I had with just the ram pressure has to be supplemented with the gas pressure, which is far bigger, and that's trying to expand. I have to get rid of the gas pressure in the equation, so I use the energy equation, PDV work. You end up with a horrible third order differential equation now, but it has a constant velocity solution, which looks like this, and for typical parameters, Fg at 0.1, all the others are fixed, of course. This thing is about 1,000 kilometers a second. So much faster, and that's the effect of adding all the energy in, which was previously lost to radiation. So what the significance of M sigma is in this picture, you go from little tiny things in the middle that are not doing much to the galaxy to something that suddenly can start pushing like crazy across the bulge. Here's a cartoon of that. That's the first case. All the things, the discontinuities are so tiny, you've got to blow them up here to even see what's going on. But once you get to the energy-driven regime, in fact, what happens is that the shock just sits at the cooling radius where it can just about cool or not. So hovering just above the cooling radius. There's an adiabatic expanding wind here, and similarly you're expanding adiabatically into the interstellar medium and forcing this stuff to move ahead of the shock. For a gamma of 5/3, a monatomic gas, this thing will be moving at 4/3 of the velocity of the shock, so a bit bigger than that 1,000 kilometers a second. In fact, what you do, if you solve it numerically, you find this constant velocity solution is an attractor. You can see all these different initial conditions, they all go to this constant velocity solution, which is around 2,000 kilometers here. If you turn off the quasar in the middle, there's still so much energy left in the bubble, it will still go, albeit it slows down, but it goes quite a long way if you look at it. It slows down, velocity drops, it's still quite high, so even long after the quasar switches off there, you can see that the stuff actually keeps on going out. So you don't have to see something in the middle for one of these things to be active. It could have been active in the past.
But it only gets to 20 kpc. In this
I'm
one.
sorry?
It only got to 20 kpc in that.
No, it's 2,000 kilometers a second.
The 20
Oh, sorry. Yeah. If you turn it off, that too. It depends how long you leave it on. So the interesting question now, if you look at carefully, you think about what's happening at this shock interface. What I've got now is a hot gas pushing into cold gas, and the cold gas is actually denser. So in terms of local gravity, gravity is acting like that, and I've got a heavy gas sitting on a light gas. Pressure balance doesn't matter, that doesn't help you. That's Rayleigh-Taylor unstable, it wants to turn over. And so it will start mixing the cold gas into the hot gas, and this is a cartoon because of course you can't calculate at this point, you're stuck. But it is actually plausible that this gas you mix in gets compressed and cools down actually to molecular temperatures. And that had better be right because that's what you actually see. So you do see objects with spectacular molecular outflows. What you also ought to see, if we had sensitive enough instruments, is that there are actually gamma rays coming out here too from the original radiation shock that was being driven. So this is the outflow velocity now, it's 4/3 of the shock velocity. And the radius is growing like this, and it's overtaking mass in this way because that's the mass inside radius r out. And that tells you the outflow mass rate, which is spectacularly high. It's thousands of solar masses per year. So this is not a prediction you can run away from very easily. And here are some observations. There are several objects now known. Markarian 231. Indeed, it's about 1,000 kilometers a second. It's only just got started. It's only measured about kiloparsec. The outflow rate is indeed of order 1,000 or more. There are others where it's even bigger. And there is another combination out of these things you can make.
That number is derived assuming spherical symmetry?
All sorts of complicated assumptions go into it. It's molecular, right? So they have to know the patchiness. It's horrible, this problem. But the comforting thing, I didn't show this, but there are several ways of doing it.
Andrew?
Yes?
we are-
Was that? Oh, that was. I thought it was a lot of geese, but it's you. The comforting thing is that you can do it lots of different ways. They tend to, even without knowing what the others got, they tend to get similar numbers from different lines. So I'm no expert there, but I think that it's clear there's a lot of gas coming out. The number you can work out from that, remember this prediction here, we should now see this as the mechanical luminosity of the outflow. Right, that's because we now didn't lose any. It came out in the shock and was then pushed into the momentum, the kinetic energy of the outflow. It's 5%. You can't really fiddle with it. Here is what the observations tell you. That all these things have been observed. They cluster around this 5% line. So it does look as though the mechanical luminosity of the outflows is about 5% of the AGN in the middle. So you can't really fiddle with that, and that seems to be a robust prediction. There is a second effect here, which, given the nature of this conference, I feel obliged to mention. The bulge will spread out spherically. Nothing happens to the disk. The disk of a galaxy, if it's there, is too dense. So nothing much happens to it, except that it feels the bulge on each side of it. This has now got gas pressure, it's not room pressure. And so it feels that, and this can pressurize the central parts of the disk and can stimulate star formation. Several people have pointed this out. So you could, in principle, accompany a quenching of the bulge with a little brief moment of happiness for the disk in which it gets some star formation, but those presumably are rather mixed together in time. I think, in view of the time, I'll have to skip forward very quickly. People have worried about what happens when things are inhomogeneous. People have suggested if you have cool blobs, these would only feel the drag of the wind, and of course dimensionally that's very similar to run pressure. The worry I have here is that drag is a difficult thing to work out, as people will know. For example, if this were a smooth, that is non-viscous, non-ripply object, it would feel no drag at all. D'Alembert's paradox, because the hot gas outside is virtually incompressible as well. So it's not absolutely obvious you get a similar result here. And similarly, there are worries about whether two fluid effects on Compton cooling would stop the cooling. My response to this is a colleague once said to me, well, Coulomb collisions may not equalise the temperatures, but something else will. So plasmas do tend to like having electrons and ions at the same temperature. But the big distinction, which I want you to take away from this talk, if you take away anything, apart from a sense of despair, is that momentum-driven means small scale, and energy-driven means big, large scale, very, very different. These things are hugely different in scale. And there is evidence for localised behaviour. I'll just put these up. But the fact that you bottle up these outflows in the middle means that the same gas has to be recycled in stars there. You can't get it away, so you've got a chance of boosting the abundances. They're also, each time you do this, you're moving around a mass in gas equivalent to the mass of the black hole. So this is an enormously magnified version of what these people try to do with supernovae, which has much less mass, in attempting to remove dark matter cusps, so it might have implications for that. We don't have enhanced star formation, so in most galaxies all the time, so we don't expect energy-driven outflow most of the time. And this two-phase thing, small then expulsion, is exactly what you need if you want to cook the metals in the middle and then expel them at large velocity into the circumgalactic medium. So I will stop there. Thank you.
Rachel?
So, from careful modeling of a number of objects now that have claims of these boost factors of 10, 20, 30
Yep.
times L over C from
Yes.
fast winds
Yes.
that clearly are arising
Yes.
at very small scale.
Yes.
What you do.
That's exactly what you get when it's mass loaded.
Yeah, exactly. So then you're not in this fast cooling regime as you
Not at all. Once they're large scale,
Oh, these
the
are not large.
what scale are they?
Well, they're seen at large scales, but they're.
Well, then they are
they're
large scale.
Very small scales, right?
No, but the ones that are small scale are only seen in the X-ray, you know, the 0.1C
Exactly.
things.
Yes,
But I don't think they're super Eddington in their thrust.
they are.
These guys are. The large scale molecular ones are a factor of 20 over
I'm not
Eddington.
talking about the molecular ones. I'm
Okay,
talking about the
I think
ones-
we need to compare notes.
All right.
So you're transporting a wind from 0.01 parsec to 10 kiloparsec, right? I presume there's a lot of energy.
No, it's already shot
But I mean,
long inside.
Well, but your wind is going from the disk into the galaxy.
It's going from the accretion disk around the black hole into the galaxy. Will shock, even in the energy-driven case, it will shock at around 10 parsecs.
But where does your wind, the 5% is not interesting unless you can transport that energy into the galaxy, right?
Yep.
Okay, so you have exquisite sensitivity to diffuse gas and the ultraviolet
Yeah.
against the continuum of the quasar. Where are these winds? What do they look like? Why have you not mentioned
The winds that you see in the X-ray,
Not in the X-ray. The X-ray, that's just some stuff going around the accretion disk that doesn't get out, right? I don't know.
well, nobody it gets
I
out.
interpret- I'm just saying, there's the UV radiation against the quasar. I should see lots of stuff moving out. So are you saying these winds are BALs, or what are they supposed to look like in the UV?
BALs are like a higher powered version of this with a higher Eddington factor. So it gets more complicated, but you can do the sums and it works.
I'm just saying there are plenty of quasars out there that show no evidence for BALs or winds.
Well, then they're probably not accreting at Eddington. They're probably not doing anything like that. It's all episodic. You know
Yeah,
that.
we can talk about this. I will show some actual data on some actual
Exactly.
10 kiloparsec winds, and I can tell you all you want to know about what else we expect to see about that.
Right? Then perhaps you, last question?
I had also a question about the dust scattering, which you
Good
did
question.
mention.
Yeah.
Rachel already
Yeah,
brought it up.
yeah. Dust scattering is very important, but very tricky to treat. Now, what people have typically done is say you hit the dust particle once, and somehow the photons are all diffused in all directions, and so you can treat it as though it was momentum driven. That's, I think, almost certainly not right. What in reality would happen was when the dust was small, you bottle up the luminosity inside, and it's now a fluid itself, it's bouncing around inside, and you push until you become transparent. And at that point, the dust then decouples and doesn't get pushed anymore. Same would be true of electron scattering. And that, in fact, may be where these so-called worm absorbers occur. It's where the electrons then decoupled in the beginning.
Where is that?
In a worm absorber, it's a few tens of parsecs. But in the dust case, my impression is that most galaxies are not, you can see into the middle of most galaxies, so dust is not blocking your view in most cases. So that, I think it can't be driving very much.
Okay. I think we probably should move on. Save some thoughts for the discussion for lunch. Thank you, Andrew.